we'll have it that way. So good afternoon. Happy Thursday. And what we will be talking about today is the next assignment, which will focus on water distribution system monitoring. So just to start, I want to talk a little bit about the factors that affect water quality. Now, you measured some water quality parameters at the tap or earlier this semester. We really at that point didn't talk about why those parameters might change, but there's a number of reasons. So in terms of what factors affect water quality, for example, one is source water. Hard water will tend to form scale, and that prevents the water from contacting the pipes. And that can play a very significant role in preventing corrosion in the system. Very, very soft water, for example, from reverse osmosis units, will tend to want to dissolve the metals to reach equilibrium, and you will see significant corrosion. And if you look at the lecture from 483 from Wednesday, you'll see some photos in that showing the extent of the corrosion. These photos were actually taken in Holmes Hall after the reverse osmosis unit, where there was significant corrosion of the iron pipes. High organic matter can result in high concentrations of disinfection byproducts. We'll talk a little bit more about those later. And they can also result in low concentrations of chlorine residuals. Water age can play a significant role, again, in water quality. The longer the water sits in the pipes, the longer time for reactions, the longer time for chlorine to decay, the longer time for any metals in the pipes to dissolve or leach into the water system, the longer the time for microorganisms to proliferate. Treatment and the water chemistry plays a significant role. So for instance, reduced pH will tend to promote corrosion, dissolution of metals in the distribution system. Temperature will also play a significant role. You saw that with the chlorine decay experiment. Higher temperatures resulted in more rapid chlorine decay. Lower temperatures, lower rates of decay. Biofilm formation is affected very much by the water chemistry. It's affected by the water age. And one of the things we're concerned about right now with buildings remaining empty is the lack of flow of water in the pipes, or the stagnation of water in the pipes, resulting in proliferation of microorganisms that can include Legionella, which can cause pneumonia. So one of the things we want to make sure right now is that as buildings open, we make sure we flush those plumbing systems to ensure that we are flushing out these microorganisms. The condition of the distribution system is very important. If there are leaks in the distribution system, then that provides a potential for microorganisms from the soil environment to infiltrate into the pipe itself and contaminate the water within. And then the distribution materials also play a significant role. So for example, is it a lead service line? Is it copper? Is it a PEX, polyethylene? So there's significant differences, and those can change the water quality in very significant ways. Now, in order to really talk about distribution systems, we need to define the distribution system. And we talk about public water systems. So a public water system is any system serving 15 or more connections or an average of 25 or more people per day for at least 60 days per year. That is the law in the U.S. Public water supplies can be publicly owned. They can be privately owned. So it really has nothing to do with ownership. It has everything to do with who that water is being supplied to. So a community water system supplies water to the same residential population year-round. City of East Lansing, Meridian Township provides water to the residents of these townships and city. That is a community water system. Board of Water and Light supplies water to Lansing. There are also other townships that purchase water from Board of Water and Light, and then they distribute it. You can also have non-transient, non-community water systems, and these regularly supply water to at least 25 of the same people at least 6 months of the year, but not to their residents. So this could be a school or a factory or a hospital that has its own water supply, but it's not providing water to any residents. MSU, because it provides water to a residential population on campus, is a community water system. And then we have transient non-community water systems, and these provide water to places where people don't reside or don't stay at for a long period of time. So this could be a campground, a rest stop. They have their own water supply, but those people that visit that facility don't stay for any long period of time. Now, when we're looking at making sure drinking water is safe, and I put safe in quotes because it's in some respects a loaded term. It's very difficult to define what exactly is safe, but under the Safe Drinking Water Act, this is what we do, how we define what we need to do in a community water supply to ensure that the water is safe for the community. So it's the responsibility of the community water system to meet safe drinking water standards. Those include both the maximum contaminant levels and treatment techniques. Some chemicals, for example, have a maximum contaminant level, chemical like benzene, arsenic, have MCLs. Others, for instance, lead, has a treatment technique. These are for chemicals that are either too difficult to analyze, or EPA has determined that it's best regulating these by what's referred to as a treatment technique. And we'll talk a little bit more about this later. Community water systems are also required to monitor. They're required to report, maintain records, and notify the public if there is any violation. And as you saw earlier this semester, they are required to annually notify the public through the water quality reports or the consumer confidence reports about the water quality. Community water systems are run by certified operator. You can't walk in and decide you're going to run a system. The operator has to be trained. The operator has to have experience, pass a number of tests, and then would be allowed to run a facility. The operator is also responsible for devising a sampling plan. That sampling plan has to be approved by the primacy agency. Every state except Wyoming has a state agency that is given primacy. They are responsible for overseeing the operation of these community water systems. In Michigan, this is the Department of Environment, Great Lakes, and Energy. So the plan will spell out where and when samples will be collected, when they will be sent to a certified testing lab. So it can't just be any lab that tests, that lab has to be certified, and how the records will be maintained. The records have to be kept for a particular length of time. That length of time really depends on the type of report. So for instance, bacteriological analyses are kept for 5 years, chemical for 10. Violations, corrective actions are kept for 3 years. So it very much depends on the type of report. Now, these records include the copies of the lab results. They include the name of the person who collected the sample. They would include who analyzed the sample or what lab analyzed the sample, where and when the samples were taken. They also include past and current violations and what steps were taken to correct those violations. And they include sanitary survey reports. And a sanitary survey report provides an opportunity for the primacy agencies, or in Michigan, EGLE, to visit the water system, educate the operator about proper monitoring and sampling procedures, and to provide technical assistance. They're a proactive public health measure and an important component of the Safe Drinking Water Act. Public water system supervision. So what do they include? They include issues regarding the source. What measures are taken to protect that source? What treatment is being used? What chemicals are being used at the plant? It will include information about the distribution system and what information is done to maintain that distribution system. How is the water being stored? What pumps are being used to pump water? How are those pumps being maintained? It will also include monitoring and reporting requirements and how the system is managed and operated, along with information about operator compliance. So what education are the operators continuing to engage in? They're required to maintain a continuous education procedure in order to maintain their license. So depending on Michigan, depending on the type of license they have, they're required to do a certain number of hours of education related to drinking water in order to maintain their knowledge as up to date as possible. We looked at consumer confidence reports earlier this semester, and you saw that community water systems are required to generate and provide these to the customers. Look back at the consumer confidence reports. Those reports that you looked at should identify where the water comes from, should identify what is in the water, at a minimum, any violations that occurred, what the consumer can do to protect the water. And you'll see that these vary significantly in terms of how detailed they are, but there should be some mention of what can you do to protect your water. Where you shouldn't dispose of chemicals. One of the things I've been doing a water survey, groundwater survey in Ingham County with a colleague, and we've been looking at water quality throughout the county. One of the things we're observing is that people are, in some cases, discharging their brine from their water softeners far too close to the well. And basically what's happening is the calcium and magnesium that is in the brine is just being recycled back into the well, and they're actually seeing higher concentrations of calcium and magnesium in their water over time. They're also seeing higher concentrations of chloride in their water because there's high concentrations of chloride in the brine from the salt. The consumer confidence reports should also outline any projects that are planned to improve the system. Those of you that are in 483 and recently did the scavenger hunt and you visited the East Lansing wastewater plant and you saw that outfall is very, very new. It was actually just constructed and installed within the last year. They've made some major changes in their supply. So that's with a wastewater system, but a water system would also have documentation of how they would improve their system. And these have to be sent to the customers by July 1 of each year. Most utilities do provide these online, and you should be able to get these for any community. So for instance, if you were looking at moving into a community in Michigan, you should be able to go online and find that consumer confidence report. And if you can't, you can then contact the plant supervisor, public health director, public works director, and they will send you a copy. So in terms of what is measured out in the distribution system, there are a number of parameters that are routinely measured. And these include disinfectants. So we'd be looking at a chlorine residual. Disinfection byproducts. These are chemicals that are formed from the reaction of the disinfectant with organic matter or inorganic matter that is present in the water. So in terms of organic matter, chlorine can react with organic matter, this is naturally occurring organic matter, to produce trihalomethanes, can produce haloacetic acids. Ozone can react with bromide that's in the water to form bromide. And there are maximum contaminant levels for each of these chemicals or groups of chemicals. For trihalomethanes, it's a group of 4 chemicals. For haloacetic acid, it's a group of 5 chemicals. For bromide, it's just bromide. We also monitor for microbials. So we monitor for coliform bacteria. These are gram-negative bacteria that are naturally occurring in the gut of intestines of all mammalian species. So we monitor for both total coliform and then also E. coli. Systems will also monitor for heterotrophic plate count. And this is just a group of bacteria that can grow on standard media. And then typically, we monitor for pH, organics, inorganics, and radionuclides. For the most part, the organics, inorganics, and radionuclides are monitored at the plant, not out in the distribution system. And then we monitor for turbidity, color, taste, and odor. Again, most of this is done at the plant rather than out in the distribution system. We monitor pressure in the distribution system. We want to ensure that at all points in the distribution system, there is at least 20 psi pressure to avoid infiltration of water and soil bacteria from around the pipe itself. And then we typically monitor for water temperature. We also have specific programs of monitoring. So we have, for instance, a wellhead protection program. All systems that use groundwater as their source are required by law to have a wellhead protection program. Michigan State has one, It has a well system, about 17, 18 wells, and they are required by law to develop a program to protect these wells from contamination. And as part of this program, the system must assess the hydrology of the wellhead zone. They must perform a risk assessment of past and future activities. So for instance, with MSU, they'd be concerned with the potential impact of agricultural runoff. As there's more development in the area, they'd also be concerned with urban runoff. If there are wells that aren't properly capped, they'd be concerned with the potential of chemicals to actually infiltrate into the groundwater because of that. And then accidental trucks and rail car spills. So we've got railroad lines through campus, concerned about the potential for a rail accident and then the impact of that on the wells. And then surface water systems also require extensive monitoring of both the source water and the treated water. Now, looking at the distribution system, we'll start here at what looks like a reservoir. So we have our source water that is transported through raw water mains. Now in Flint, or actually in Genesee County, not in Flint itself, but in Genesee County, with the Karagandhi Water Project, what they've done is they've built a raw water main from Lake Huron about 50 miles across the state to just outside of Flint, I think it's Flint Township, and they've built a water treatment system. So they have a large water main that is transmitting water from Lake Huron to Genesee County. And then they have a water treatment plant at Genesee County. So we have a water treatment plant. We then have a distribution main. So the water goes from the treatment plant often into a storage tank. So for instance, in Michigan State, we have that new elevated storage tank. The water goes from the treatment plant out into the elevated storage tank, and then from elevated storage, it is distributed to campus. So then we have a distribution transmission main. In the case of the Lansing Board of Water and Light, they have a water treatment plant, they have water storage, they have a distribution main, and for the townships that purchase water from the Lansing Board of Water and Light, that water would flow through a trunk main to that community. And then as we move through the distribution system, our pipes are getting smaller and smaller. We have trunk mains here. We have distribution mains, and then mains right out to the community. Once we get to the home level, typically we refer to these as service lines. So it goes all the way from our transmission mains down to the service line. Transmission mains can be on the order of 6 feet in diameter. Your service line is typically on the order of about 3/4 of an inch in diameter. So I mentioned previously that we monitor for disinfectant byproducts. Under the disinfection byproduct rule, community water systems are required to monitor both disinfectant levels, and there are established maximum residual disinfectant level goals and maximum residual disinfectant levels. These have been established for chlorine, chloramine, and chlorine dioxide. For instance, for chlorine, it's 4 milligrams per liter as the maximum residual disinfectant level. We also, as I mentioned, there are maximum contaminant levels for, I mentioned the total trihalomethanes. These are the 4 trihalomethanes, the 5 haloacetic acids, also for chlorite, which can be formed from chlorine dioxide. It's a toxic byproduct, and for bromate. And we also have MCLGs, goals that have been established. So we've got both goals and levels. And the systems are required to develop and implement a monitoring plan. This monitoring plan would include specific locations of where they sample, the schedules for collecting samples. So for instance, trihalomethanes and haloacetic acids have to be sampled quarterly. They're sampled at the same location where bacterial samples are collected. And they typically are going to be further out in the distribution system, areas with longer age, because those are the areas where there's more likely for a reaction to have occurred and more likely to have higher concentrations of trihalomethanes and haloacetic acids. You're basically looking at for the worst case because you want to protect that population. And based on the results, they can then calculate compliance with these regulatory limits. Under the surface water treatment rule, end systems that are using a source determined to be a groundwater under the influence of surface water. So for instance, in the East Lansing Meridian Township water treatment system, they have lagoons that are used to dewater the softening sludge. That water from those lagoons have been traditionally pumped back to the headworks of that plant. So now it's gone from being a groundwater system to a groundwater under the direct influence of surface water. Then they've been undergoing significant changes in their treatment system to eliminate that recycle in order to avoid being a system that is under the direct influence of surface water. But surface water systems, like groundwater systems, have significant levels of significant requirements for monitoring. So for instance, the filters must be continuously monitored for filter effluent turbidity. And with regard to disinfection, the systems must monitor the chlorine residual, and what they're monitoring is free chlorine residual, which is the same measurement that you did in one of the labs. And they have to ensure that the free chlorine residual at the entry point to the distribution system is not less than 0.2 milligrams per liter. And for all systems that have greater than 3,300 customers, then they have to do continuous monitoring. They also have to monitor for disinfectants in the distribution system. Now, this is just another schematic of a distribution system. It's similar to what we saw before. We have our water treatment plant, we have our transmission main, our distribution main, and then we have our water mains out into the community. And what you see here is this service line. And this is what with regard to this next assignment, this is the part that is pertinent to us right now. Typically, the service line is essentially divided in half with a curb stop in the middle. The curb stop is, you can find that with a breast, typically a breastplate, and that is where water can be shut off to a residence. The area on the street side of that curb stop is typically referred to as the public side. So this is owned by the utility. On the homeowner side of the curb stop, this is typically privately owned, which means that, for instance, if you have a leak here, it's the homeowner's responsibility to fix it. If you have a leak here, it is the utility's responsibility. It also means, for instance, if you have a lead service line here, and for the most part, in most places, if you wanted to have that replaced, that would be the responsibility of the homeowner. The lead and copper rule is the law that governs, regulates the level of lead in our drinking water systems in the U.S. And systems are required to validate whether or not their water is corrosive enough to potentially release lead or copper into the treated water. As I mentioned, there are no maximum contaminant levels for lead or copper. We focus on lead service lines and copper pipes with lead solder. The number of samples is dependent on the number of customers. So for instance, in Flint in 2014, there were greater than 100,000 people, and they had to sample 100 locations. When that population decreased to less than 100,000, then they were only required to sample, it's either 63 or 66 samples, I now forget. And I should have looked it up and I didn't. The number of samples, as I mentioned, the number of samples is dependent on the number of customers. They sample every 3 years unless they've made a significant change in their water treatment process, in which case they have to sample every 6 months until they have at least 2 sets of samples showing that the 90th percentile is at or less than the 15 part per billion action level. That 15 part per billion level is not a health-based standard. It was a standard set in 1990 at a level that EPA and the utilities thought could be met and would help notify and inform a utility if they had not optimized corrosion control. So that 90th percentile means that 90% of the samples must have a concentration at or less than 15 parts per billion. There is no upper limit. So if you had 100 samples and one of them were, that's 90% were, let's say less than, at 14 or less, you've met that limit. But you could also have a system, one sample, a couple samples at 300 or 30,000. You still meet the rule based on this requirement. That's beginning to change. I think we'll see some significant changes, hopefully in the next few years, really as what happened in Flint came to the forefront and an attempt was made to strengthen this law. Michigan has now set that 90th percentile at 12. So there was a real debate whether it would be 10, but it was set at 12. And Michigan is also mandating the removal of lead service lines. Okay, so let's look at what happened in Flint. And I'm not going to go into the details really of the treatment process. This is a much bigger story than what I'm going to focus on today. Today, what I really want to focus in on is the monitoring aspects of what happened in Flint. So, City of Flint has been distributing water to the community since the late 1800s. In 1887, the City of Flint mandated the use of lead service lines for both water and gas lines. The fact that they did for water lines really affected this whole story that we'll look at. Now, the City of Flint was treating and distributing water up to 1967. 1967, Flint was an industrial city, burgeoning, flourishing industrial environment. We had auto manufacturing and all of the associated facilities with that. There was a concern at that point in time that the Flint River could not produce sufficient water for the community and the industry. So at that point, they began purchasing water from what was then Detroit Water and Sewer Department, and they did so until from 1967. And they did until April 2014. Now, between 1967 and 2014, the economy has suffered significantly. There's been a significant exodus of population from Flint as a result of the loss of manufacturing. And there was a significant confrontational debate between the city and Detroit Water regarding the water charges. In this years before 2011 to 2014, Flint is suffering economically, and at that point, Governor Snyder installs an emergency manager to the city. That emergency manager assumes all financial responsibility, basically all decision-making for the city. There is still a mayor, there is still a city council, but in effect, they have no authority to make decisions. In April 2014, the city changed from purchasing water from Detroit Water and Sewer to treating Flint River water using that plant that had essentially been mothballed since 1967. It had been operated in part a few times a year, but that water that it had produced had always been discharged back into the Flint River, was never distributed to the community. Now, as part of the long-term 2 enhanced surface water treatment rule, filtered systems serving at least 10,000 people must collect samples for Cryptosporidium, E. coli, and turbidity for at least 24 months before distributing water. To my knowledge, that never happened. And as a result, in the city of Flint, there was no data that was available then to be used to, for instance, to determine the disinfection requirements for that water. Now, the data that I'm providing you here is actually data collected during the plant operation. The monthly operating reports, part of this monitoring requirements include raw water quality. So this is data from June and December in these monthly operating reports. And what you can see, for instance, is the bacteria counts vary significantly from between 1,000 to almost 15,000 colony-forming units per 100 mLs. Total coliforms, similar, it's very significant range. The high concentrations are typically related to storm events, surface water runoff into the river, and potential contamination with microorganisms. Temperature ranged from about 1.4 degrees to almost 26 degrees C. That means that has a significant impact on the operation of the plant. It also has a significant impact on water quality in the distribution system. At higher temperatures, chlorine will decay much more rapidly. So you'll have more challenge at maintaining a chlorine residual throughout that disinfection system. The Flint River is often described as being corrosive. The chloride levels in the Flint River were really not that high. However, they increased up to a factor of, in some cases, more than double, or actually triple at the lower levels, up to about 100 milligrams per liter, because of the ferric chloride that was added and the chlorine gas. Fluoride was typically within acceptable limits. Turbidity also highly variable from about 2 to 22. Again, those high levels related to storm events, and the organic carbon from about 6 to 10 milligrams of carbon per liter. And this is an indication of potential problems with meeting those trihalomethane and haloacetic acid regulations. So by mid-May of 2014, there were significant complaints. Initially, these were to the US EPA, and they were actually regarding rashes. By June, people started complaining and attending city council meetings, reporting that the water was bluish or yellow, yellowish in color. The blue could have been high copper levels. We don't know, but it could have been. They reported that the water smelled like sewage, had unpleasant odors. The chlorine residuals varied significantly in the distribution system. And as you see here, in June of 2014, roughly 14% of the samples collected did not have a chlorine residual. The regulatory limit is 5% for 2 consecutive months. So they didn't exceed the regulatory limit because this July, the levels did decrease, but again, they increased again in August, and this is a significant concern in that they're not maintaining a stable chlorine residual throughout the disinfection system. We can also look at this in terms of the free chlorine levels. There were 8 sampling locations in the distribution system, roughly here, where they switch from purchasing water from Detroit Water and Sewer to treating water in Flint and then distributing that. And what you see is that there's fairly consistent levels. This is the standard deviation, fairly low standard deviation within these 8 monitoring stations. There's some that's cyclic because of the temperature differences, but it's consistent. And then they switch. Notice the standard deviation increases significantly. That means that there's wide variations in chlorine residuals in the distribution system, and there's wide variations in the actual chlorine residual with high levels in some cases and almost non-detect in others. It was in October of 2015 that they switched back to purchasing water, and this was a increase done. It was in conjunction with, or under the guidance of EGLE, then MDEQ, to try and flush out the system, ensure that all areas of the distribution system had sufficient chlorine residual. As a result of those low levels of chlorine, or the percentage non-detects, in summer of 2014, there were 3 boil water alerts spanning a 22-day period of time. This is extremely unusual. I can think of a handful in the 30-something years that I've lived in the area here. So 3 in a summer, as I mentioned, is highly unusual. Now, when you have these boil water alerts, when you have low levels of chlorine disinfectants, what do? You increase your disinfectant levels. Well, as a result of increasing the disinfectant levels, what you see are high levels of trihalomethanes. By December of 2014, then MDEQ, Department of Environmental Quality, informed the city that they would violate the disinfection byproduct rule because of the high levels of trihalomethanes. And at that point, decisions were made to change the operation of the plant. They were bypassing around the softening units. They stopped that bypass, and they started looking at adding granular activated carbon. That was actually added in the summer of 2015. They were also required to do lead sampling under the lead and copper rule. And this is just a summary of results from 2001. And what you see, and if we look at this period of time from 2005 to 2011, you see that the 90th percentile levels are below 2. They're actually below the, or at the detection limit. The detection limit was 2 at this point here and 1 here. So they're at the detection limit. And they report 0 samples exceeding 15 parts per billion. And then they switch. Now, as I mentioned, because of that switch, they had to sample every 6 months. And what you see is an increase in the lead levels and the percentage exceeding. So we have, in terms of the percentage exceeding, we have about 2% exceeding 15 parts per billion and a 90th percentile level of 6. And then the following 6-month period, that percentage increases to about, I think it was about 9%. And what you see here is that the 90th percentile was about 12.6. It actually would have exceeded 15. However, there were 2 samples. One was in a bathroom, and I can't remember where the other one was, but those samples were discarded as being improperly taken, because the one was done in a bathroom, not a kitchen. And as I mentioned, I can't remember the other one, why that was discarded. But those samples were both discarded, and that brought the level below 15. All right, well, let's then look at the study that you will do. So this is kind of a combination assignment, lab, but it's going to count as an assignment. So what you will be doing, and you'll do this in your team, you will be making recommendations regarding flushing residential plumbing, and this is why I've gone through the discussion about distribution systems. But you'll be making recommendations regarding residential plumbing to ensure that any water that is consumed is not likely to have been sitting stagnant in the pipes and will not potentially contain high concentrations of lead and copper. Now, obviously, we can't measure lead and copper right now, but we are going to do our best to come up with some recommendations. So what you will be doing is you'll be determining the volume of water in the premise plumbing. You'll look at both hot and cold water, and then you'll determine the volume of water that needs to be flushed from the pipes in order to bring in water from the water main. In order to do this, you will need your temperature probe. You'll need a 1-cup measuring cup or an empty wide mouth container or jug of a known volume, some measuring tape, a caliper or ruler to measure the diameter of your plumbing, and the conductivity probe. So the way that I've written this is to allow multiple options. The way I set up the groups is you should have at least one member of your group that is living in a single family home. So that student has a little bit more work to do, so maybe go easy on them on some of the writing. The others will have some calculations to do. So what you will do is you will choose a water fixture in your home that's readily used for consuming water, typically a kitchen faucet. You're going to turn the tap on full. You ideally want to do this early in the morning before everybody else has woken. Using the thermometer, you're going to measure and record the temperature at intervals of no greater than about 1 minute. If you have a housemate that's willing to help you record data, you might want to ask for their help. I found it easiest to have a 1 liter wide mouth container, so for instance, a water bottle, that I could turn the tap on full, collect 1 liter of water, shut off the tap, record the time to collect the 1 liter, and measure the temperature and conductivity of the water. Then I could discard the container and I could repeat until the temperature stabilized. Since it's getting colder, you should find that the temperature of the water is warmer initially, and then it should decrease, stabilize probably around 15 degrees C, at least in the US. Use the same technique for the hot water. Be careful with the hot water that you don't scald yourself, but you'll do the same thing. You're going to turn the hot water tap on full, and initially it should be colder. And then do the cold water first, and then do the hot water. And you're going to monitor that temperature until the hot water temperature stabilizes. And you can measure, you don't have to measure conductivity, but since you've got the probe, if you want, you can also measure conductivity and see if the conductivity changes. What you then will do is you're going to measure as best you can the length of plumbing from the fixture to the meter. So you're going to have to find the meter. It will typically be located in the basement, typically at the front of the house. If you can find your curb stop, it probably is a straight run from the curb stop to the home, and it's just on the other side of the wall. You're going to determine the diameter of the pipe. Since you can only determine the outside diameter, you're going to use the pipe schedule to estimate the inner diameter. We're going to assume that we don't have significant scaling of our pipes, so that we're going to assume that the volume is the volume from the pipe schedule. And you can use this information to determine the volume of the water in the plumbing system. And you'll compare the volumes calculated and the volumes measured. You'll also locate your water heater, and you'll calculate or determine the volume of water in your water heater. Often people tend to, or some people will drink hot water from the tap. I want you to think about that, and would you make any different recommendations once you've done this experiment? You'll also need to determine the length of your service line. So you'll determine the length from the point where the water enters the home, so that's on the opposite side of your meter. So it's on the outside wall to the curb stop. So you'll see a brass plate. You want to do this sooner. Well, we only have a week anyway, but you don't want to do this after a snowstorm because it's going to be harder to find that curb stop. So hopefully, I don't think we're planning any snow in the next week, but you might want to think about that, especially if you're living in an area that is more likely to get snow. Assume your service line has a 3/4 inch inside diameter, and you'll determine the volume of water in the service line. Now, if you're living in an apartment, obviously this is much more difficult to do. So what I have given you is a schematic of the piping in a home. And I've given you information about the pipe materials. So for instance, for student 1 living in an apartment, the assumption is that all of your premise plumbing is copper. And I've given you some lengths and diameters, and then you will make similar calculations. If you want to try and do the measurements, you're more than welcome to do that. But I designed this so that you didn't have to, because it's so much more difficult in order to do that in an apartment. If you're living in a duplex, you can do the same set of experiments as someone living in a single family home. Because your duplex is essentially plumbed very much the same way. And for the student 2 living in an apartment, I've set it up with PEX piping. So again, you're going to have to use the standard pipe schedule. So you're going to have to find out what a standard pipe schedule looks like. I've given you the link. And you're really, in this case, just determining volumes of water in the premise plumbing. So your report will take the form of a 1 to 2 page memo. It should not be any longer than 2 pages. And you are providing a recommendation to the New Zealand Ministry of Health regarding the protection of public health based on exposure to lead in drinking water. Why New Zealand? It's a cool country. I did my sabbatical there in 2018, and they actually have a program called Flush a Mug, and they promote that, for instance, when you get up in the morning, you flush a mug of water, discard that, and then you can consume the next mug of water. The question is that protective of public health? If not, what should the New Zealand Ministry of Health be recommending for its citizens and residents of New Zealand? So you will be developing recommendations. If this isn't sufficient, then you will be developing a flushing protocol to protect public health. Make sure that your flushing protocol addresses differences in premise plumbing, variations that you may have observed, so that what you have designing is in fact protective of public health. All reports must include an appendix, and the appendix will include the data analysis and discussion items. So in the report, I talk about some discussion and data analysis that I would like you to do. That goes in the appendix if it's not in the memo itself. But your memo should be no more than 2 pages long. All reports should have a supplementary section, same as before, with your scanned images of your raw data, photos of you documenting your work, and raw data and calculations. In terms of data analysis, what I would like to see is that you plot the temperatures measured as a function of time and volume. And want to be sure that you properly label the axes, include a legend and a figure caption. The figure caption should be sufficient that a reader can look at the figure, read the caption, and understand your data without having to go to the main text. And then you'll report the length of time that it took the warm water to reach the tap, You'll, in this, talk about the length of time to stabilize for the cold water, same with the hot water. And you'll compare your results. For instance, actually I need to change this. I initially had 2 different fixtures. You only have to do 1 fixture, but compare the results for both your calculations and your measurements. Okay, I didn't want you to have to do 1 tap. Got 1 there. So all group members, in the group, there should be 1 group member that's living in a single family home or a duplex. That group member will be providing their data to the rest of the group. That's why I said go easy on them. Maybe go easy on them for report writing, because they've got a little bit more work to do. The other group members will be doing the analysis, the calculations for the copper pipe or PACs. So you should, all your group as a group, you should have a composite data from the single family home and from the calculations for copper pipe and PACs. And I tried early on when I set up the groups, I tried to make sure that every group had someone live in a single family home. If you don't, let me know and we'll figure out something. So the lab is due in a week. That becomes a problem. We'll deal with it, but hopefully we can get this done in a week. And just kind of to put up the rest of the semester schedule, as I mentioned, I reduced the number of labs from 6 to 4. This I'm counting as a assignment. Lab 4 will be pH and conductivity of soil. And as I mentioned, you're going to want to save either mason jars, spaghetti sauce jars, or like a 1 quart Gatorade bottles. You'll need 4 of these to determine the soil type. The revised syllabus is posted on LonCappa, and I'll be working on writing up the requirements for the final project within the next couple weeks, and we will continue with the weekly extra credit participation questions. If you have questions as you start the lab, please let me know. Always happy to answer any questions that you may have.